Welcome, engineering statics students. This is a semi-live problem solving dealing with centroid and center of mass, namely center of mass for this problem. And we'll start with a little review of the problem setup. This is excerpted from the Hibbler 14th edition of Engineering Statics. And what we have here is a hemisphere that consists of basically little flat disks of varying density, where the density of the disks is related to how high they are. So the density is a linear function of z. So this upper disk weighs a lot more than the lower disk because, well, maybe not weighs a lot more. It has much higher density. May not weigh more because it's definitely smaller. And so what we're asked to do is find the center of mass of this spherical or hemispherical body. So we're going to go back to do that. We're going to go back to a little quick review of spherical coordinates because it is a hemisphere. So it's kind of just crying out to be described with spherical coordinates. So to do that, we're going to do a quick review of how we define a point in a sphere versus Cartesian coordinates. So we've got our XYZ Cartesian axis over here with some angles defined. And so this is a little review of calculus or advanced algebra wherever you ran into that. So we have a radius vector going from the origin to some point that is on the surface of some sphere of radius r. Hey, this should look very close to the radius from the origin to some point in a body for which we're defining a centroid. So reinforcing that concept. And this radius vector is forming an angle phi with the z-axis. So we can project that down onto the xy plane and get a radius vector a that is within the xy plane that is related to the angle phi by its sine. So basically we're looking at this and this are basically the same line there, and we've now defined a plane, the ZA plane here. So A is going to be described by r sine phi. So if we look down onto the xy plane or anything parallel to it, we can define an angle theta that's sweeping around within that plane, and then we can define our x-coordinate as a function of a and our angle theta. So we can define x as a cosine theta, and we can define y as a sine theta. So if we were in cylindrical coordinates, we would just have an r vector and a z. And a would effectively be r. But because we're in spherical coordinates, our a is actually a function of r and phi. Just simple geometry, but we kind of have two right triangles instead of one. So this should maybe be reminding you of a Pythagorean theorem in 3D where we've got this projected line that is forming the diagonal of one end of a 3D rectangular body. Except here we have a sphere. So we can define x, y, and z in terms of r, phi, and theta. So x is going to be a cosine theta, where a is r sine phi. So x is going to be r sine phi cosine theta. And phi, of course, is coming, is 0 for a radius vector straight up parallel to the z-axis, and then would be 2 pi if it's laying down in the xy plane. Y is going to be a cosine theta, where again a is r sine phi, so we have r sine phi sine theta. And then z is r cosine phi, so it's this side of this triangle. And of course we can define our r vector as x squared plus y squared plus z squared, just like we would for any other 3D right triangle. Okay, so having done that, we're going to move over to a quick review of our spherical volume element. And I know this drawing seems kind of crazy. I've tried to do a bit of a 3D little volume element, but I've attempted to show how we have a differential side to what becomes like a little rounded 3D box. So we've got in our XY plane, we've got two curves, and we've got a dr on one side, and then we have an r d theta on the other side. So if we're going to define the area, this would just be r dr d theta, which would be like our polar area of a little area element. If we were in cylindrical coordinates, we would just go straight up and define a little box. So we would have r dr d theta dz, but we don't have straight up in that extra dimension. We have a curve because we're defining basically a little chunk of a sphere. So instead of a dz, our upright side is actually going to be a d theta. So, and r d phi on the other side. So I've had those mixed up. Sorry, we have a d theta on the bottom, and r d phi on the top. So we end up with a volume element that's r d phi times r sine phi, which would be a d theta. So this is a dr. So this is one dimension of our little volume element. This is another dimension, and that's another dimension. So we have like a little sort of rounded cube. So we end up with r times r squared, sine phi, d theta dr. So this is our spherical volume element for any sphere. So that was a little bit of a review of basic spherical coordinates there. So that's essential if we're going to start adding up things in a sphere, especially one where we have a density that's itself dependent on one of our dimensions. Okay. So we were told that the density is itself a function of z. So now we can define z in terms of r and phi, two things that we're going to integrate when we integrate over our whole volume. So with that in place, we can now define our density in terms of our spherical coordinates. Instead of kz, we have k r cosine phi. Now, rather than having a volume element, which would have been great for centroid, but because we want center of mass, we got to have a mass element. We can remember that our little element of mass is our density times our little element of volume, where the density is specific to that particular element of volume. So all we have to do is multiply our kr cosine phi density times our volume element up here, and we get a little bit of a long expression. So we end up with 1k, we end up with r cubed, and then we have a sine phi from up here, and we have a cosine phi from the density expression, d phi d theta dr. Okay, so we can use this and integrate through. So this is good practice, because the first thing we're going to need for the radius vector to our center of mass is the actual mass of the hemisphere. And so we're going to go 1 over that mass and then multiply that by our radius vector integrated over the whole mass with respect to dm, mass, which of course, because we can express our radius vector in its components, and I'll put some unit vectors on here. R is, of course, we can do x in the I hat direction plus y in the j hat direction plus z in the k hat direction. Break that vector up and then express it as the integral of a sum. And then we'll evaluate each one of these separately and divide by mass, and we'll get components of that radius vector from the origin, which is right here, to wherever it may be. Now, based on symmetry alone, this is a sphere. The density is only varying in the z direction. We're pretty sure that the centroid and the center of mass are going to be the same for the x and the y. So they should be at x equals 0 and y equals 0. So we're going to just integrate and evaluate one of those just to check ourselves, to kind of make sure we're using our spherical coordinates right. And then the one that's going to give us probably our unique answer is going to be our z coordinate, and we'll work that out live. But we'll just walk through something that we need to know ahead of time, which is our total mass. So coming over to this little kind of sidebar, we're going to integrate our r from the center all the way out to the actual radius of the hemisphere, and I'm calling that big R here. I'm going to integrate theta all the way around, and I'm going to integrate pi over 2, and that should give me the whole sphere. So because I'm going for mass, I'm going to use this expression. So I'm going to integrate over all of my 3 spherical coordinate differential elements the expression that gives me mass. So this is basically the integral over the mass dm. A lot of numbers to mean basically integral over the mass dm. That's another way of writing this whole thing. So we're just going to take a quick step through this. We integrate from the inside out. So we're going to integrate all the terms that depend on phi with respect to phi. So we've got basically sine phi, cosine phi, which is easy to integrate because if we had sine squared of phi, we would bring the 2 down, and we'd end up with sine phi, and then we would have to take the derivative of sine, which is cosine, and then we would get our integrand up here. So the integrand, the integral of our phi components is just basically 1/2, because we're going to evaluate this between 0 and 1/2. So if we put in, pi over 2. We put pi over 2 in for phi. Sine of pi over 2 is 1, multiply by 1/2. Sine squared of 1 is still 1. And then, of course, sine of 0 is 0. So we just end up with 1/2. So we end up with k r cubed over 2. Now we're going to integrate with respect to phi. So we don't have any terms, with respect to theta. We don't have any terms that are theta dependent, just basically a constant. So we just end up with theta evaluated at its limits of integration. So we're just going to end up with 2 pi minus 0 is 2 pi. So now we have a 2 pi times k divided by 2 times r cubed. So that just gives us k pi. And we're going to integrate times r cubed. We're going to integrate that with respect to r. And so we're going to end up with r over 4 times k times pi evaluated between 0 and big R. So we get k, which was our constant in our density expression, times pi over 4 times the radius of the whole hemisphere, and this is our mass expression. So when you see mass, it's this. Okay. So we're going to try this out, and we're going to look at evaluating kind of as a check, because we have an idea of where we think the center of mass is. And I'm going to make a little correction here. I'm going to use different expression. I am not, x bar would normally refer to centroid, and we are very much looking at mass here because we've included that density expression. So our center of mass in the x direction times mass is going to be equal to the integral over the mass of x dm. So that's this part of this overall expression. So I'm looking at one component of the overall radius to the center of mass, COM is center of mass. So I'm going to drop in my expression for x, which is r sine phi cosine theta here. And then I'm going to multiply that by, or I'm going to integrate that with respect to mass, dm. So now I've got my big dm expression. And I've broken out the parts that have a function, and then my components, my variables with respect to which I'm integrating. Simplified it a little bit here. Pulled out the r parts, the phi parts, and the theta parts. And so now I'm gonna go ahead and integrate that, and let's see if we end up with a zero term. So I'm gonna start out with r is going to go from 0 to r. I'm going to integrate theta from 0 to 2 pi, and I'm going to integrate phi from 0 to pi over 2. So for now, I'm going to keep my variables a little bit separated. I have cosine theta, and then I have my sine squared phi cosine phi d phi d theta dr. Okay, so I'm going to start with this. So if I integrate this with respect to phi, because this is the only term that is phi dependent, the rest just going to act like a constant right along. So I'm going to get, I could write this as 1/3 sine cubed of phi integrated between 0 and pi over 2. So if I took the derivative of this, the 3 would come down and multiply, giving me a constant 1, leaving me with a sine squared. Then I would have to multiply by the derivative of the argument of that term raised to a power. So that would be the derivative of a sine, which is cosine, which would give me my integrand up here. So that's a check. And if I express this with the limits of integration, I'm going to get sine cubed of pi over 2, which is 1 cubed minus 0 times 1/3, so that equals 1/3. So now I have the integral from 0 to r, integral of from 0 to 2 pi of k r to the 4th over 3, none of which is theta dependent, times cosine theta d theta dr. So now we're integrating cosine theta with respect to theta, which would give us, what would we have to take the derivative of to get cosine? Sine theta evaluated between 0 and 2 pi. So sine of 2 pi is 0, minus sine of 0 is 0. That becomes 0, which now we have zeroed basically the entire integrand out. Therefore, we can say that x sub c times mass equals 0. So the x-centroid is going to be at 0, which is exactly what we predicted. So that's a good check that that our expressions for our volume element, our incorporation of our density expression in spherical coordinates, and our limits of integration to cover the whole hemisphere, we're all working correctly with our definitions of center of mass. So now ready to move forward. I'm going to erase this. So we kind of knew what that answer was going to be. But that gave us some confidence to move forward with our z direction. And hopefully if you've seen some other centroid and center of mass problems, you'll notice that the crux really was the definition of the volume element. And that's pretty nice this time because it was standard spherical coordinates. But again, that's probably the toughest part of any kind of center of mass or centroid problem, is defining a differential volume element that's in terms that that's meaningful for the problem. So we kind of had to do something where we defined our x, y, and z because we wanted the center of mass in terms of Cartesian coordinates, and we had a density function that was in a Cartesian expression, but we had a body that was just crying out for spherical coordinates. So this step here and the definition of the volume element really were probably the most important parts of this problem. So let's go for our z center of mass. So I'm going to express this, make it a little simpler. If I multiply the mass times z center of mass, that should equal the integral over the whole mass of z dm, which should equal, I'm going to just go ahead and put in all the expressions. Our limits of integration here for our r, theta, and phi, because we're going to end up with those at the end of the integral. Now we've got z, which is r cosine phi. And now we have dm, which is k r cubed times sine phi cosine phi d phi d theta dr. So let's rearrange some terms to make this a little bit easier so we can integrate with respect to the functions that we need to integrate with respect to in the right order, not miss a term, which is pretty easy to do when we have so many. So we got our limits of integration again. So I'm going to collect all the r terms and the k together, so I can see I have a k cubed coming from my dm, my differential mass, and then I picked up another r as part of my z expression with my z dm, part of my center of mass definition. So I'm going to have r to the fourth times k. I don't have any theta dependent terms, unlike in our previous one, because z is only dependent on phi. It doesn't have any theta dependence. And in our mass definition, just make sure we don't have any. We don't have any, because again, that was also dependent on z with our density expression, and we didn't have a theta term in our volume expression. We're just making really sure we didn't. Thetas and phi's look pretty similar sometimes, so we're making sure we didn't mix them up. So we've got a cosine phi, and a sine phi. So we have cosine squared phi sine phi, which is again looking like it hopefully will be pretty easy to integrate. Seeing a little chain rule in there. D phi, d theta, dr. Okay, so we're going to integrate from the inside out, and we're going to impose our limits of integration. So we're going to start by integrating with respect to phi. So what would we have to take the derivative of to get cosine squared phi sine phi? So we could start with, again, it's going to be a cubed term. So we're going to have something on the order of 1/3 cosine cubed of phi. So do we need a negative sign? If we took the derivative of this, with the 3 would come down, we'd end up with a cosine squared of phi. Then we'd take the derivative of cosine phi, and that would give us negative sine phi, which we don't have a negative up here, so we need to put another negative to offset that. And that becomes important. And we're going to evaluate that between pi over 2 and 0. So we're going to start with a pi over 2 limit of integration, substitute in for phi. That's going to make this term 0. Then we're going to subtract from that 0 in the cosine term, which gives us 1. 1/3. We're going to subtract a negative 1/3, which should give us positive 1/3 for that term. So that should allow us to write this as integral from 0 to r, integral from 0 to 2 pi of k r to the 4th over 3 d theta dr. So this whole phi terms ended up being 1/3 when we evaluated it over its limits of integration. We have no terms that are dependent on theta, so it's just a constant. So we can express this as 0 to r of k r to the 4th over 3, all a constant from the standpoint of theta. Theta evaluated between 0 and 2 pi, which of course is just 2 pi. So we're down to one integral only. So now I'm going to collect all the constant terms. We've accumulated a 2 pi, we had a k from our density expression divided by 3 times r to the 4th dr, which should give us 2 pi k over this r to the 4th. When we integrate it, we'll get a 1/5 r to the 5th. So the 5 will multiply by the 3. We'll end up with 15 in the denominator, and we'll put in our upper limit of integration. We'll end up with r to the 5th. So that is this expression. So if we want our z-centroid, we have to take our 2 pi k r to the 5th over 15 and divide the mass of the entire hemisphere, which is like multiplying by its inverse. This will make it easier to cancel. K pi r to the 4th, and we're going to hope to goodness that we get something that's in linear units, because we need a position on the z-axis. So our pi's will cancel. We're going to get all of our r's cancel except 1. We're at a 1. K's will cancel. So we're going to end up with 2 times 4 is 8/15 r. So a little over half, which very, very different than what we would have expected with uniform density, which would have definitely put us somewhere much closer to the bottom. So much more of the volume of that hemisphere is distributed near the bottom, but because the density is scaling upwards relative to our z direction, so proportional to cosine phi and r, that's offsetting and raising the center of mass versus the centroid. So basically, key to this problem: first, express your coordinate systems properly. So we know we need to express our center of mass in terms of x, y, and z in this case, and we're given a Cartesian expression for density. So, but yet we have something that is really kind of screaming for cylindrical coordinates. It's okay. We just need to basically create a coordinate transform for ourselves. Easy to do that graphically. Go ahead and reference, good reference if you've forgotten how to do this. Pull up any calculus book or an online calculus tutorial and look for spherical coordinates, triple integrals. You'll find this graph showing phi, r, and theta, and it's pretty easy to use some simple trig at that point to create these expressions, and then your last task is to define your volume element, which is less difficult once you remember that your theta dependent side is going to have an a multiplier, not an r. After that, it's basically use your transforms to plug and chug any xyz expression into an r theta phi and apply the definition of center of mass, and have fun with an integration review. If you are not familiar using multiple integrals to define a volume or to define any kind of entity, this is a great combination with our definition of center of mass, given that we have multiple different axes that define where it is. And so when we use something like a double or triple integral, we are literally defining what we want in terms of each of its components. So in this case, the triple integral really kind of anchored the thought of where we're going in positioning that center of mass, and it made the expression a lot easier. This looks like a big gnarly expression, but in terms of any one of the variables with respect to which we're integrating, they're pretty simple integrals, and you only do them one at a time. So that is it for this example. So it's a good example of center of mass and ways to properly use two different coordinate systems.